Hello, everyone, and thank you to the organisers for inviting me to give this talk. So this session is about quantum technology in transition, so a transition from the laboratories of academia to commercialization and industry. And my talk in particular is charting this transition as it's been happening in Singapore. So I was previously at the Centre for Quantum Technologies at the National University of Singapore, and now I'm CTO and co-founder at SpeQtral, a spin-out company from the Spooky Labs group at CQT. So this talk is about that transition to some extent. It's about everything that's happened in this field of quantum communications for the last 10 years or so in Singapore, and where it's ended up to today with SpeQtral. So this talk covers the beginnings in sort of free space QKD experiments that led on to the formation of CQT itself, the past missions flown at CQT, current mission in orbit, Spooky 1, and the space to ground QKD missions that will come out of that, as well as some other topics around the area of entanglement in CubeSats. So starting from the beginning, this is pre-2010 at the National University of Singapore. So the Centre for Quantum Technologies is this building here, and the founding director, and in fact the director until last year, was Professor Arthur Eckert, who is of course the inventor of entanglement-based quantum key distribution. So CQT at the time was one of 5 research centres, national research centres that was built. There's now several more, and in that time several spin-out companies have been formed, Atom Ionics in quantum sensing, Entropica and Horizon in quantum computing, and S15 and SpeQtral in quantum communications. And the speciality, at least amongst the quantum communication side, is really in entanglement, perhaps partly due to our director. But entanglement also has, we feel, the broadest applications to the future of quantum technologies and quantum communications in particular. You can start with quantum key distribution and lead on to other technologies, quantum clock synchronization, repeaters, and ultimately a quantum internet of shared entanglement all over the globe to leverage on the various quantum devices that we hope the future will bring. So the first experiments back in 2006 timeframe were on this 1.5 kilometer free space QKD link across the campus, and this was done using the hardware like this above, BBO, SPDC, and this was then done in daylight in 2009. And this was really the precursor to the space missions, which is the main topic of the Spooky Lab group. So these first space missions were around correlated photon sources, photon pair sources. This video shows a summary of the miniaturization process. So starting off with those large lab tables full of optics devices and supporting electronics, and the sort of regular maintenance required by human operators that characterize the free space link and quantum light sources. We've been working over the time after that to miniaturize this onto a small PCB board. So miniaturizing the electronics, miniaturizing the optics components, and integrating it into this package that was small enough to hold in the palm of your hand. So the first versions of these space-based sources were what we called correlated photon sources. So they weren't producing, or at least they weren't characterizing entanglement in the pairs of photons they produced. They were just producing photon pairs. And we called these devices SpeQs, the small photon entangling quantum systems. And these first generation were to test the sort of miniaturization capabilities and characterize their robustness, the capability to maintain optical alignment, the detection systems, the Geiger mode avalanche photodiodes, how we could stabilize their readouts under varying temperatures, and investigate the radiation impact on them. And you can see also how tightly integrated the electronics were. So all of the optics in the black box on the top there, with the electronics on the reverse side of that. So let's take a look inside those first photon pair sources. So there's the high voltage power supplies that we need to bias the detectors. There's the 405 nanometer laser diode, the SPDC crystals, and the avalanche photodiodes in the detector module at the side there. So looking at the source section, there's our blue photons. Most of them just go straight through and are dumped at the beam dump. But every so often, a pair of red photons are born in the BBO crystals, and those are sent through to the detector module, where the coincidence detection events are recorded. So if you just have a single crystal, you can use that to make your correlated photon pairs. So every so often, a blue photon splits into 2 down conversion photons. If there's the 2 crystals, we can then create the polarization entangled photon pairs. And that's represented by the sort of fuzziness around the pairs of photons there, with the idea that when the entangled photon pairs are separated, they're separated by wavelength there in the detection module, the entanglement, the spooky correlation between them is preserved and can be measured by correlations in the polarization measurements on those 2 detectors. So this is now looking inside the correlated photon source, the block diagram, and you see the various elements there. The blue laser light being turned into the red photon pairs at the 0.5 there, the SPDC crystal, the various elements to align the beam and send it to the detectors. So this correlated photon source package was tested on a number of missions. So the first being this weather balloon. It's actually two weather balloon missions in 2012 and 2013. And this tested the temperature stabilization as well as some of the shock sensitivity as the balloon bursts as a big kind of shock impulse. In 2014, it was integrated into the GOMEX-2 mission, and this mission was launched from the US. This is on the launch pad, and then there it is taking off. And a few seconds later, this happened, and that rocket was, of course, lost. So the rocket might have been lost, but actually, a few days later, the satellite, the satellite payload, was found on the beach nearby the launch site. We were actually able to recover the photon source. We turned it on, and we found that the performance, well, the source and the satellite were still working, and the performance was basically the same as it had been previously. These charts show the voltage that we had to apply to the liquid crystal polarization rotator to make the polarization measurements, and you can see there's a slight lag. On one side, we have to apply a bit more voltage than we did previously, but the functionality of the device is still completely intact there. So the next mission, the Galassia mission, that did make it to orbit. This is a 2U CubeSat, so this is 20 centimeter CubeSat there. And that device was operational in space. In fact, it's still in space. And the performance in orbit was pretty much the same as the performance on the ground. So this gave us confidence that the basic systems, the basic electronics and alignment systems were working as we intended. So that brings us on to the mission which we're currently operating, and that's the SpeQtral 3U CubeSat. So this was launched in 2019, and this has this sort of a later version of the entangled photon source. So this entangled photon source has the two crystals and is producing polarization entangled photons, and those are characterized at the two detectors next to it. So we call this mission SpeQtral, and there's the mission patch with Einstein that's scared of these entangled spooky ghosts. So inside that device, you can see the optical layout there, and also sort of mechanical structure to support all of that. So we had to, the alignment requirements of this device are stricter than the pure correlated photon pair source that we saw previously. So to maintain the entanglement between the photons, the polarization entanglement, we have to make sure that the whole unit is mechanically very stable. And with a satellite in space, which is getting very hot when it's in sunlight and very cold when it's in the Earth's shadow, this takes a bit of consideration. So you can see on the left there the structure that we've built around that. So at the bottom there's the side wall of the spacecraft, and then between that aluminium plate and the entangled photon source, there's these three mounting blades. So the entangled photon source is largely made up of titanium, which was a requirement of the flexing stages, and therefore of the whole unit. And to avoid issues of flexing from mismatches of the coefficient of thermal expansion, we have these triangular flexing blades that absorb any of this flexing caused by the outside of the spacecraft. And they also help to maintain, to just sort of isolate the temperature of the payload from the satellite. So this was launched in 2019, in June. So yeah, nearly 2 years in space now. And it's functioning as it was on the ground pretty much. So we can see here, these are again the polarization curves. We've now got 4 of them, one for each of the 4 polarizations: horizontal, diagonal, vertical, and anti-diagonal. And yeah, we can see that that there is no loss of performance when it's operating in space. So this gives us confidence that we can use these concepts or these techniques that we've developed for full space-to-ground QKD missions. And for the last few years, we've been working on the designs for this, with the intention of launching these in the 23-24 time frame. So the sort of setup looks something like this. Well, this is one of several different configurations. This one's from the paper cited below there, and the spacecraft, we're actually using a 12U size spacecraft now, but you have to have these pointing beacons to maintain the optical link between the ground station and the satellite, and then the entangled photons are sent over that link. So the entangled photon source that we're using for these latest missions, actually based on a PBKTP crystal, allows for a much brighter signal, but we can still leverage a lot of the work that was done on the previous devices. And you can find more information about the source in that paper there. The satellite, this is quite an early design of the satellite. It's actually moved on quite a bit from since then. So Ralph's based in the UK. I've been working on the satellite design, but it's now a 12U package. And this shows you some of the sorts of elements that need to be considered when building a satellite. So ADCS, the Attitude Determination Control System, this needs to be very high accuracy for tracking the ground station. The optical payload, as it's called here, is the telescope module, which attaches to the quantum light source that beams the photons down to the ground station. This has to have its own sort of fine steering mechanism within that to control the pointing of the beam to a higher accuracy than the satellite platform pointing can be by itself. And then various other power and communications subsystems that are needed inside the spacecraft. And the delivery of quantum keys looks something like this. So the satellite's in low Earth orbit, so it's sort of 500 kilometers above the Earth. And as it passes over the ground station, it needs to first establish these high accuracy pointing to the ground station, so pointing the satellite body, and then fine steering the beam, so that so this is achieved with those pointing beacons. So beacons shining down, but also pointing up from the ground station. Then the qubits, the entangled photons can be sent over that same link. And afterwards, the classical information can be downlinked for post-processing. And the concept is that this can be used for a trusted node key exchange. So you perform this quantum key distribution operation over two separate ground stations. You have the key for both ground stations stored inside the satellite. The satellite can then XOR those two keys together and broadcast that XOR publicly over RF without giving away any secrets. And the two ground stations A and B can then do a reverse operation on that XOR to determine what the other ground station's key is. This can then be used for secure communications between those two sites. So that's a sort of summary of the source development work. I'll just use the remaining time to talk about a few sort of side projects on the same sort of theme. So these are photon key distribution and inter-satellite quantum communications and satellite QKD constellations. So the idea of photon key distribution was really looking at the question, like, what is if quantum key distribution is the most secure form of communication or optical communication between satellite and ground station, and laser comms is sort of the other extreme in terms of optical comms, then is there anything in the middle? For example, if you're if you're using laser comms, you still have to worry about eavesdroppers that might be around your ground station or around your satellite that can sample the beam, that can receive like scattered light from that laser beam, and they would still be able to determine your communications. So if you're still concerned about this, but if you're not concerned about attackers directly in the line of your beam, then is there something that you can do which is more efficient than quantum key distribution? Because of course quantum key distribution will protect you even against this eavesdropper in the middle. But if you're convinced that you can see the satellite and there's no one between you and the satellite, what can you do? And so that was the context for this paper. Satellite communications when man-in-the-middle attacks are excluded. We called it PKD, photon key distribution. And the idea is that if on the left there, you can see the key rates as a function of loss for various QKD schemes. If you take that same kind of hardware and exclude the possibility of a man in the middle, so you have some other mechanism for convincing yourself that there's no one in the middle, maybe radar or just optically looking, then you can continue to do, well, you can continue to do this kind of communication at greater losses, and with some increase of key rate, because you're not having to discard all the measurements can be made in the same basis. That's what that paper was looking at. And we've also spent a while thinking about inter-satellite quantum communications. So this might have applications to refreshing keys between GNSS satellites, or for sort of unspoofable covert clock synchronization between satellites. And there's a paper out here that we did together with the University of New South Wales in Canberra, looking at a sort of mission study for 2 satellites, each with entangled photon sources that could do quantum communication sort of bidirectionally between them, sort of particularly relevant to quantum clock synchronization. And they have quite a small terminal, I guess. And this graph's looking at the kind of separations you could achieve for different accuracies of that pointing and tracking system. So yeah, if you're limited to 10 microradians, then there's supports a link separation of 450 kilometers. But if you can improve that pointing and tracking, then you can go to much longer separations. Then thinking about where this inter-satellite links might be relevant, we've also did some work in satellite constellation modeling and using inter-satellite links in those constellations. This Acta Astronautica paper, where we look at, so there's different types of constellations. If you have this sort of string of pearls, all the satellites in one plane, or if you have satellites on different planes, how that looks like. So here we are now as SpeQtral. We are a spin-out company from National University of Singapore, and we're working to commercialize all of the above. So in the short term, we have various sort of hardware developments that we've made that we can sell as products. In the long term, we would like to sell QKD keys, and we're interested in partners for proof of concept demonstrations to show secure, quantum secured end-to-end communications. We have investment from some of the investors on the top there, and we are hiring. So if you are interested in joining us in Singapore, particularly looking for software developers and electronics, optoelectronics engineers, then do get in touch. And thank you for listening.